Welcome back to the deep dive. If you are tracking the cutting edge of large model architecture, you know that the simple, powerful residual connection has reigned supreme for nearly a decade.
Absolutely.
But today, we are cracking open a technical paper that proposes a potentially fundamental shift: hyperconnections, or HC.
Mm.
This is a novel structural component designed to serve as a direct and potentially superior replacement for the ubiquitous residual block.
That's absolutely right. For those of you deep in model architecture, this deep dive is highly focused. Our mission here is to provide a comprehensive, professional overview of hyperconnections,
Right.
strictly based on the source paper's concepts, results, and analysis. We are really just dissecting the architecture that claims to offer performance gains with almost zero overhead.
Okay, let's unpack this and set the stage. Residual connections, the backbone of ResNets and, the essential layer in every transformer,
Yeah.
were instrumental in solving the gradient vanishing problem.
Oh, completely.
They allowed us to build the massive, deep architectures we rely on today. But they are not perfect.
No, not at all. They exhibit what the paper terms the seesaw effect, this inherent trade-off that has plagued model scaling.
The seesaw effect.
Exactly. When you try to ensure gradient stability, you end up compromising the uniqueness of your feature representations, and, well, vice versa. It's a constrained optimization problem that's literally built into the architecture.
Could you elaborate on how that manifests in the standard variants we use every day?
Certainly. So take prenorm, where normalization happens before the residual block. It's fantastic for gradient flow. The signal propagates easily through deep layers.
Right.
However, this ease comes at a cost: representation collapse. The hidden features across adjacent layers become, well, too similar.
Meaning the deeper layers are doing less work.
They're contributing diminishing returns in terms of novel feature extraction. They essentially stop learning new things.
And if we flip that, post-norm tries to solve the feature redundancy issue.
Exactly. Post-norm applies normalization after the output. By reducing the direct, strong influence of the hidden state on subsequent layers, it successfully alleviates representation collapse.
The features become more distinct.
Yes. But this inevitably reintroduces the problem of vanishing gradients, making training unstable or, slower, particularly in very deep models.
So you're stuck.
You are. And the core insight the HEC paper operates on is that both variants are fundamentally constrained because the connection strength, the weight given to the residual path versus the main path, is rigidly predefined. That fixed strength is what HEC aims to break.
So the conceptual leap, then, is to let the network learn that strength itself.
Precisely. To allow the network to autonomously learn and optimize that connection strength. Hyperconnections achieve this by introducing two new learnable components: depth connections and width connections.
And the architecture starts by fundamentally changing the information flow at the layer input.
It does. Instead of a single stream, HC expands the network's input into n copies. And you should think of this not as increasing the dimension of the feature vector, but as splitting the information stream into n parallel channels within that specific layer.
Which form what they call the hyperhidden matrix.
Exactly. And crucially, the paper finds that n greater than 1 is not just an option, it's a necessary design requirement to see performance gains over the baseline.
That makes sense.
Yeah.
If n is 1, you haven't really escaped the core constraint of the residual block. So within these n parallel channels, how do the depth and width connections function?
They function as a kind of routing and weighting mechanism. The depth connections are the generalization of the residual path.
Okay.
They are scalar weights, labeled beta I, that assign a trainable importance factor between the previous layer's output and each of the new hyperhidden vectors. This is the mechanism that learns the optimal layer skip strength.
Addressing the seesaw effect vertically.
Right. And the width connections handle the horizontal information exchange.
You got it. Using weights they call alpha ij, these connections facilitate lateral information exchange between those n hidden vectors within the same layer.
So the channels can talk to each other.
Precisely. It allows the newly created channels to communicate and consolidate information before passing it to the next layer. And the entire system is governed by a single, comprehensive router matrix, HC.
Okay, so that's the structural overview. We have the mechanics. But how did they make those connections actually learn? Were the weights static or dynamic?
That brings us to the two major functional implementations explored in the paper. The first, static hyperconnections, or SHC, is pretty straightforward.
The alpha and beta weights are just standard trainable scalars.
Yes. They are fixed after training, offering a learned architectural bias. And the second, the more intriguing approach, is the dynamic variant.
Yes, dynamic hyperconnections, DHC. This is where the connection weights, the routing parameters, dynamically depend on the specific input hyperhidden matrix H.
Wait, so the weights themselves are computed on the fly for each input token?
For each token, it's done via a linear transformation, a normalization step, and a tan activation, all scaled by a small learnable factor, SPETA or ESO.
So the connection strength isn't just learned during training, it actually changes for every token. How do they stabilize that? I mean, that sounds like it could cause massive volatility during backpropagation.
That small, learnable scaling factor, S, is the key stabilization mechanism.
Oh.
By initializing S close to 0, the dynamic connections start weak, which keeps the gradient flow stable early on. As training progresses, the network learns the optimal magnitude for that dynamic effect.
And critically, the paper shows that even with this complex dynamic calculation, the computational footprint is.
It's genuinely negligible.
That's the most remarkable part. For the ULMA 1B DHC by 4 model, we are talking about a mere, plus 0.03349% increase in total parameters.
And only a 0.2% increase in total FLOPs per token compared to the baseline?
It's basically a free upgrade. We are achieving massive architectural flexibility and performance gains for an increase in complexity that is effectively zero in a production environment.
So moving from the mechanics to the theoretical foundation, the paper provides a really strong rationale for why HC is architecturally superior.
Okay.
And it emphasizes its generality and flexibility.
Let's start with that generalization argument. How does HC mathematically encompass existing residual structures?
The paper proves that HC is a true superset. Both pre-norm and post-norm residual connections can be expressed as specific, non-trainable hyperconnection matrices, assuming an expansion rate n1.
So they're just special cases of HC.
Exactly. For pre-norm, the HC matrix simplifies to a hard-coded identity flow. For post-norm, the coefficients, while still fixed, become dependent on the variances of the input and output. The takeaway is clear. HE gives the network the freedom to learn the optimal coefficients that pre-norm and post-norm are forced to hardcode.
That establishes AC as a direct successor. But the flexibility of n being greater than 1 introduces an entirely new degree of freedom, leading to this idea of sequential parallel duality.
Yes. This duality means HC allows the network to learn the optimal layer arrangement, not just the connection strength.
Interesting.
Traditionally, you have to choose either a purely sequential layer arrangement, like standard deep stacking, or a highly parallel one, like parallel transformer blocks.
And HC can blend them.
It creates a soft, trainable mechanism for mixing them. A specific configuration of the HC matrix can perfectly recreate a purely sequential classic residual arrangement.
Okay.
Conversely, defining alternating HC matrices for odd and even layers results in a parallel arrangement every 2 layers, structurally mimicking parallel transformer blocks.
So the network isn't constrained to picking one, it learns the optimal hybrid.
And, vitally, with dynamic HC, that mixture can adapt dynamically for each input token, optimizing the computational path based on the data flowing through.
The idea that the network can self-organize its macro architecture on the fly is a major shift. This raises a pretty important question. What did the practical learning process reveal about these theoretical choices when applied to massive language models during training?
The empirical evidence, primarily conducted on the Olmo family of models dense 1B and 7B variants, and mixture of experts models trained on 500 billion tokens, is quite compelling. HC provides consistent, measurable advantages across the board.
I found the results on the mixture of experts models, specifically the Olmo 1B7B DHC by 4 variant, to be the most dramatic demonstration of HC's power.
They were very strong.
According to Figure 1, the DHC model converged 1.8 times faster than the baseline. That's a massive acceleration in wall clock time and cost reduction.
And the performance gains are not subtle. It showed a reduction in C4 invalidation loss of 0.028, which indicates superior generalization. But the real headline is the notable improvement of 6 points on ARC challenge compared to the baseline.
A 6-point leap. For those focused on reasoning, that means the model is deriving deeper, more abstract, and less token-specific knowledge.
It's a true architectural enhancement to intelligence, not just memorization.
And the dense model results confirm this enhanced ability. The Olmo 7B DHC by 4 consistently outperformed the baseline across PPL metrics, improving V2 PPL by nearly zero point 0.3.
And crucially, the DHC model demonstrated noticeably more stable training. It exhibited fewer severe loss spikes compared to the residual baseline, which speaks directly to its success in robustly managing gradients.
The ablation studies then provided the necessary validation for the design decisions we discussed earlier.
Right, they really backed up the theory.
Let's review the expansion rate N.
The paper established that N1 performs inferior to the baseline. This confirms that simply adding learnable weights to a standard residual path isn't enough. You need the expansion. But when N is 2 or greater, performance improves significantly, with N4 generally achieving the best trade-off between cost and performance. This conclusively validates the necessity of introducing multiple hidden vectors, those parallel channels, to successfully escape the seesaw effect.
And the other critical component, the width connections, WC.
Absolutely vital. Ablating the trainability of the width connections, that lateral information flow, causes significant performance decline.
How significant?
It led to a V2 loss increase of 0.021. This confirms that splitting the stream isn't enough. Those streams have to communicate within the same layer to synthesize the optimal features before passing them on.
Okay, so now to the visualizations, which offer a window into how hyperconnections work internally. The paper analyzed the hidden state representations using cosine similarity. The baseline pre-norm model showed high similarity between features in adjacent layers, the classic signature of representation collapse.
It did. But in contrast, what did the HC model show?
HC models exhibited significantly lower and wider ranging similarity between features across adjacent layers.
Which is direct, measurable evidence that HC successfully mitigates representation collapse.
Right. It ensures that each successive layer contributes distinct, non-redundant information to the overall transformation.
And here's where it gets really interesting, looking at the structural patterns the network learned. Examining the unfolded connection matrices that dictate flow reveals a signature lambda-shaped pattern.
This lambda shape is the architectural genius of the learned system. Think of it like a river delta. The pattern shows that the contribution of feeders from layers long in the past quickly decays.
Which is a characteristic of post-norm's long-term decay.
Exactly.
Yeah.
But the immediate layer outputs, the bottom layers of the lambda, are frequently and strongly accessed by the subsequent layer. This combines the best traits, long-term gradient stability from post-norm, with the immediate easy flow from recent layers of pre-norm.
And crucially, the visualization provides a structural explanation for an optimization we often try to hard-code, the input embedding contribution.
That's right. The visualizations confirmed that the contribution of the original input word embedding is reduced or effectively eliminated from the final layer input.
And why is that beneficial?
Because when the last layer computes the next token prediction, you are the result of the entire, deep, nonlinear transformation, not a noisy reminder of the starting word, especially when you're using tied word embeddings.
So HEC learned to eliminate this noisy input bias automatically.
It did. And finally, the direct evidence of learned parallelism.
Yes. The paper confirmed that HEC can learn dynamic parallel arrangements. They observed PTB-like patterns, for instance, the connection matrix showing layer 11 having minimal contribution to the layer 12 input.
That structural disengagement implies that the network decided, on its own, to run those two steps in a parallel configuration for optimal computation,
providing direct empirical proof of the sequential parallel duality in action.
To solidify the generality and robustness of hyperconnections, the paper extended the method beyond LLMs to computer vision tasks, specifically VIT for classification and DIT for image generation.
And the vision results were equally impressive. It really underlines the architectural rather than task-specific nature of this innovation.
For image classification, the VT16 large DHC by 2 achieved a top 1 accuracy improvement of 2.69% relative to the baseline, reaching 79.94%. This showed significant gains, particularly at the larger scale models.
And for image generation, the DIT models incorporating HC achieved comparable performance metrics to DIT baselines that had 50% more parameters.
Which isn't just a performance bump, it's an efficiency argument.
Absolutely. HC allows smaller models to punch far above their weight in terms of parameter count.
To summarize the massive contribution of this work, hyperconnections successfully address the persistent seesaw effect of residuals by introducing learnable dynamic connection strengths with negligible overhead.
Right.
And the method provides consistent, measurable performance improvement and significantly faster convergence across diverse, state-of-the-art architectures, whether pre-training LLMs dense or MoE or tackling complex vision tasks.
The final takeaway for me is how this learned mechanism changes the whole conversation about architectural design. By allowing the network to dynamically adjust its internal layer arrangement, HC effectively learned a configuration that transcends these fixed, human-defined architectural rules.
So it's no longer about whether you choose sequential or parallel.
Exactly. The network figures out the optimal structural bias, layer by layer, input by input.
So what does this all mean for you, the researcher or architect working on the cutting edge? The final provocative thought for you to consider. If future deep learning models can autonomously evolve their optimal internal architecture using fundamental learned mechanisms like hyperconnections, what other long-standing architectural assumptions beyond just residual connections, perhaps activation functions or normalization layers, might be ready for replacement by dynamic learned parameters?